Okay, so this is problem 13.2 out of Taylor's Classical Mechanics textbook. And before I get into this problem, if you wouldn't mind giving a like and subscribing, I'll post more solutions out of this textbook. So problem 13.3 says, consider the Atwood machine in figure 13.2, which I have here. But suppose the pulley is a uniform disk of mass m and radius r. Use x as your generalized coordinate, write down the Lagrangian, the generalized momentum, and the Hamiltonian. Find Hamilton's equations and use them to find the acceleration. And maybe it'd be easier if I move my mic over here. So to begin with, for a uniform disk, our moment of inertia I is 1/2 mr squared. Okay. And the kinetic energy associated with the rotation, so the rotational is 1/2 I omega squared. And omega is just x dot over the radius, because that's your angular velocity. So we can substitute these two equations, and we get 1/2 times 1/2 mr squared times x dot squared over r squared. Obviously the r squareds cancel and you get 1/4 m x dot squared. That's important because we need to write down the Lagrangian, and the Lagrangian is the difference between your kinetic energy and your potential energy. Okay? So the kinetic energy has the kinetic energy of the two blocks plus the rotational kinetic energy of our pulley. So we'll start with our kinetic energy. For kinetic energy, we'll have 1/2 m1 x dot squared plus 1/2 m2 x dot squared plus 1/4 capital M x dot squared. Okay, so that is our kinetic energy. Now our potential energy, that's going to be no different from before. It'll be m2 minus m1 times gx. So this doesn't change at all from the previous problem. And all it is the gravitational potential energy of mass 2 and mass 1. Okay. Alright, then our Lagrangian, gave that a little accent, is 1/2 x dot squared times m1 plus m2 plus 1/2 capital M, and then plus m1 minus m2 gx. Okay, so from here, let's see, they wanted us to find the Lagrangian, which we did, and now we want to find the generalized momentum. And the way that we find that is we take the derivative of our Lagrangian with respect to x dot. And that's usually called px. So only the kinetic energy term, pretty easy there. It's just going to be x dot times m1 plus m2 plus 1/2 capital M. Okay, so that's our conjugate momentum. We just have to take the partial derivative, and now we need to find Hamilton's equation, and that's pretty straightforward. It's just like the equation here, px dot minus L, px dot, and then our Lagrangian we already have, right? So that would just be minus 1/2 x dot squared times m1 plus m2 plus 1/2 m minus gx m1 minus m2. Now what we could do is we can actually write our x dot in terms of our momentum from this equation right here. Okay, so we could also say that x dot is equal to px over m1 plus m2 plus 1/2 capital M. And we can plug that into here. We can square it and plug it into here. Okay, and then what do we get? We're going to get p squared over m1 plus m2 plus 1/2 big M minus 1/2 times px squared over this denominator squared, but that's going to cancel with one term right here. So I'm just going to write it as m1 plus m2 plus 1/2 m minus gx m1 minus m2. Okay, that's equal to this. And then the Hamiltonian, just combining them, would be p squared over 2 times m1 plus m2 plus 1/2 m, and then minus gx m1 minus m2. Okay, so that's our Hamiltonian. Now we can find our Hamiltonian equations of motion. So x dot is the partial derivative of our Hamiltonian with respect to the momentum. So that's pretty, I think, straightforward. The two will cancel there, and we'll get p over m1 plus m2 plus 1/2 m. And then likewise, p dot is minus the partial derivative of our Hamiltonian with respect to x. So that'll be now positive g times m1 minus m2. Okay. So if we want to find x double dot, we can just take the time derivative of both sides, and you let x double dot equals p dot divided by m1 plus m2 plus 1/2 big M. And p dot is here, so we can put that into here, and you get g times m1 minus m2 all divided by m1 plus m2 plus 1/2 capital M. So that's how you solve this problem. You just have to include one extra kinetic energy term, so it changes your Lagrangian, and that of course will change your Hamiltonian. It'll change your momentum and your acceleration. So that's how you do that problem. If that helped, please like and subscribe, and I'll post more. Thank you.